Color Affecting Emissivity Using Thermoelectricity, The Story of My Science Fair Project by Yakubek. Dark colors absorb heat and light colors reflect heat. A lot of people know this, but what's not considered as much is whether dark or light colors emit heat better. At least that's what I wondered about when I began my science fair project. I did my research, of course, and I found that dark colors apparently emitted heat better than light colors did. This didn't make much sense to me. Shouldn't black colors retain heat if they absorb it well? That's why I chose the topic for my experiment, color affecting emissivity. The problem, though, was how to measure the transfer of heat in a realistic way. So I researched some more, and I discovered two things that would help with my experiment: Peltier devices and heat sinks. A Peltier device uses thermoelectricity to heat or cool objects. It's basically a small and precise heater. Heat sinks, which are often used in computer systems, prevent damage by dispersing extra heat. And so, combining the idea, atoms, and information, I came up with my hypothesis. If a black heatsink and a white heatsink are identically heated, then the black sink will lose much more heat than the white sink does. Besides the heat sinks, one white, one black, and the Peltier device with its power supply, I needed a stopwatch and thermometer. I would also need heat sink compound to reduce air contact and a clamp to hold the experiment together. After planning out my experiment, I set the heat sinks upright, smeared the Peltier device with compound, and then clamped all three together firmly. Then I plugged in the necessary cables. I placed the thermometer in the white heat sink and turned on the power. Once the white sink reached 60.4 degrees Celsius, I turned the power off and started my stopwatch. I recorded the sink's temperature every minute. When 5 minutes had passed, I waited for the sink to cool down before unclamping, removing the Peltier device, flipping it around, and reclamping. Then I moved the thermometer to the black heat sink and repeated the experiment. And after I did that, I repeated the whole thing again and again in case of any inconsistencies. My data showed that in Trial 1, the line graphs for the black sinks noticeably dipped faster than those of the white sinks. In Trial 2 and Trial 3, the same result occurred. The bar graphs showing the total loss of heat were also conclusive. Black heat sinks always lost more heat than white heat sinks. In fact, all of the data seemed to match my hypothesis. Well, almost. It turned out that the black sinks emitted on average only 2.1 degrees Celsius, or about 4 degrees Fahrenheit, more than the white heat sinks. I was expecting a greater difference, maybe double or triple that, but still the black heat sinks consistently performed better than the white ones. Black coloring of heat sinks makes a sizable, though not huge, difference. My hypothesis was correct in that the black heat sink emitted more heat. However, the black sinks did not emit much more heat, although this depends on your point of view. My project taught me about the effects of color in the physical world. The concept of my experiment used in real life to increase and decrease heat emissions is a very important topic. It can even be applied to things like global warming. If I ever continued with this project, I would want to experiment with measuring efficiency of colored heat sinks in actual electrical systems.